Okay, let's wait for a few minutes and then I'll start. Okay. So we'll wait for a few minutes and then I'll start. Okay, so we can start actually. So if you have any questions regarding the assignment or last lecture or any lecture actually, you can please unmute yourself and ask. So regarding this, I mean the upcoming assignment as well as the previous assignments, let's say. So there is no questions.
Hello.
Yeah, sure.
I wanted to ask that whether in the exams, do we have to do the entire revision for important parts? And
Sorry, you are not audible clearly. Can you repeat again?
so I was asked. Hello.
Yeah, yeah, you are audible now.
Yeah. I was asking that during the written exams, do we have to solve the entire derivations and do the entire steps, or because the derivations will be very long? So I had a doubt how the I am doing the exams for the first time. I don't know how the derivation should be done in the NPTEL courses.
Mhm. So I think the big derivation will not be there. There can be some small derivations actually. Okay, and so the questions will mostly be from assignments, either assignments or the assignment like questions. It will not be very out of context questions. Okay, yeah. But small derivation can be there. It's not. Uh, it depends on the course instructor. We do not have any. I do not have any information how he wants to conduct things. But these courses is generally not the answers. Sorry, the questions are generally not only MCQ type. There might be few MCQ types, or just one line or two line or three line answers. No derivation, nothing. Just write the equation and done. And there can be some small derivation as well. But mostly
Okay,
it will be within the boundary of the questions being asked.
because all the assignments are derivations, so that's why I was
Right,
asking.
Right. So this is the, I mean, this is a very advanced course actually. Okay. Uh, Within the E2X, the full rigor of the course is also not possible, but a lot of things is being covered. So, yeah, we do not really have that so many assignment like problems, uh,
Yeah,
like
problems are very
right, like other basic courses, preliminary solid state physics and so on. Okay. Uh, Most of the problems are the only problems where we can sort of analytically derive and do some numerics, small numerics, and then understand things. The rest of the problem is even more higher level actually. Okay, so yeah,
yeah.
yeah. So and then assignments are solvable, right? I mean, it's not very difficult if we follow the lectures.
No, assignments are actually from the lectures only, so
Right,
it's
right.
mostly easy to run.
Yeah, that's why I am sort of trying to take a different path. There is no point in repeating the same thing again here. Yeah. Okay, so in the last class, what we did is that we tried to understand what happens when we apply magnetic field uh, in in uh, in a two-dimensional electron gas, right? And so to summarize, what we found is that this kind of, so let's say imagine we have a Hamiltonian of this kind. This is a two-dimensional free electron gas. It only have momentum of px and py. And then once we apply magnetic field, then there is a Hamiltonian. I mean, the magnetic field enters into the Hamiltonian, and primarily in these momentums, where this pi x and pi y are the modified momentum, and those are defined like this, where A is the vector potential, okay, uh, which contains the magnetic field. So if you take curl of A, then you will get the magnetic field. And we solved this Hamiltonian. It turns out that this Hamiltonian can be mapped to the harmonic oscillator case that we have solved in basic quantum mechanics course. And like in harmonic oscillator case, we had two operator, right? A and A dagger. These are ladder operators of this n equal to 1, I mean 0, 1, 2, 3, 4. These are the I mean integer energy steps. Uh, but then what we have said in the last lecture is that if you talk about the two-dimensional electron gas, let's say, so I have a two-dimensional electron gas. There are 4 degrees of freedom, right? So this is, let's say, x, this was y. So so an electron here, right? It has some position along x direction and y direction. So it's a coordinate x and y, and it is also having some momentum, right? Px and py. So there are primarily 4 degrees of freedom associated with each electron. And then when we constructed the quantized Hamiltonian after the magnetic field was applied, what we saw was that energy wave function. So this will be something somewhere here. Yeah. So the energy wave function, or rather Hamiltonian. Let me go to, yeah. So this part. So the Hamiltonian can be written in terms of these 2 degrees of freedom. One is A and A dagger. So these are two ladder operators. Again, the conventional uh, harmonic oscillator. And then once you solve these ladder operators, A dagger is the number operator, and then use number operator associated with the each quantized energy level n, and this was the energy, right? It's a two-dimensional electron gas, so this was n equal to 0, n equal to 1, n equal to 2, and so on. Okay. What we missed in the previous class itself, we highlighted that the degrees of freedom must not change. It remains constant even before applying magnetic field and after applying magnetic field. Then, in search of those hidden degrees of freedom, let's say, because we started with this I mean x and y position and px py momentum. What we found that we only having in the Hamiltonian, we are only having A dagger A, right? But then we constructed. It turns out that we can construct two, I mean, similar operators B and B dagger, and we did quite a bit of algebra. and then found that the wave function for the nth eigenstate, right, nth energy level can be written like this, where in the wave function the B operator comes into the picture, whereas I mean, there is no B operator in the energy. Okay, energy is simply n plus half h bar omega c. So what this necessarily means is that there are many different wave function which have uh, I mean this n and m. So there are many wave function which have same energy n plus half, whereas I mean, so basically that means that these energy levels are degenerate. Okay, many wave function have the same energy which only depends on n, and we found that this m is another quantum number which corresponds to this B dagger, which was not present in the energy or the Hamiltonian. Okay, uh, and then we solved. I mean, in doing this, we solved in the symmetric gauge picture. We did quite a bit of algebra, but the crux of the story was this, that if you operate a dagger on a valid wave function psi n and m, you go from n equal to 0 state, let's say, to n equal to 1. So once you operate this raising operator, you go from one energy state to another energy state. But if you operate B dagger, it is also a creation operator on the psi nm. You remain at n equal to 0, or wherever you start with. Let's say you are operating on the n equal to 1 state, you remain at n equal to 1 state, but then m increases by 1. Although because n doesn't appear in the energy expression, you are still remaining at the n equal to 1 state or n equal to 2 state, wherever you start with, but then you are increasing the m. Okay. Today, in the first part, we'll try to understand what do we physically what is being represented by m, because n we know n is just the energy levels, right? You increase n from 0 to 1, you are going from one step to another step, you are increasing the energy. Or if you decrease n, similarly you are decreasing the energy. But then we do not have any physical picture of m. Okay, uh, in the first half of the talk, depending on how much time it takes, we'll understand the physical uh, significance of m, what it implies. And the reason we're doing all of this is that it will be helpful in understanding the quantum Hall effect. Okay. In the next lecture, I will try to cover up the quantum Hall effect. It turns out that I mean, understand the quantum Hall effect, you need at least, I mean, these Landau level pictures, okay, that we are studying from the last class. And then you need something called edge state. Some bit of it we already did in the first 2 3 classes when we studied topological insulator in terms of SSH model, and then something called disorder. Okay, and these three things are needed. Okay, so we're just covering up the basics as much as we can, so that all these three will combine to have an comprehensive understanding of quantum Hall effect. Okay, so that's the end goal. Okay, so for today, I will be mostly focusing on what is the physical significance of M, and then towards the end, if I get time, I will introduce the quantum Hall effect and what are the physics that we are trying to understand. Okay, okay. So let me just simplify. Okay, so what we had is that initially we had this kind of, let's say, 2D electron gas. Okay, where electron can, I mean, perform cyclotron motion. We had applied a perpendicular magnetic field, and this is along the x direction, this is, let's say, along y direction. And this was, so this was our case. And what we found, if we solve this problem, 2D free electron gas in the presence of magnetic field, what we found was something like this: n equal to 0 state, n equal to 1 energy state, n equal to 2, n equal to 3, and so on. And the gap between these two consecutive energy levels was h bar omega c, where h bar omega c is nothing but h bar ev by m. Okay. Okay. And then in the last lecture itself, what we have found that psi nm, which we will also write like this in the shorthand notation n comma m, uh, was let me see. Yeah. So this was the state. Okay. So this was the state. So a dagger to the power n, b dagger to the power m, and then root over n factorial, m factorial, and then 0, 0 is the vacuum state. Now, if we write this I mean wave function, uh, we can actually, it turns out that the we can write in terms of associated legendary polynomial. Okay, these details we are not doing because that will lead us to more heavy mathematics. But I'll actually list few references from where we can read. It turns out that if so, what we had is that simply a dagger of n, b dagger of m, and root over n factorial m factorial, and then this was the 0, 0 state. Okay, and it can also be written as minus 1 to the power n root over 2 pi root over n factorial by 2 to the power m plus n factorial, and then e to the power minus z square by 4 lb square, and then z to the power m, uh, and l n m r square by 2. Okay, or rather z square by 2, then I think lb square. Okay, so usually we write we take lb as 1, and lb was the magnetic length, by the way, so this has a unit of h bar by root over h bar by eb. So we usually omit this lb square, okay, just for our convenience. So everything is written in units of lb. Okay, and also sometimes we replace mod z by r. Okay, remember z was x plus iy, or rather x minus iy, I think. Yeah, and we replace by I. So r is also in the xy plane. Okay, so this is r, and z is also one in the xy plane. So we just map it to the plane. Now the question that we ask is that, and these are the, I mean, uh, associated legendary polynomial, I think. Yeah, or Lagure. This I have to check actually.
Hello.
Yeah,
Uh, yeah. Uh, so the solution was actually we represented the solution in terms of harmonic oscillator, right?
right, right.
So the wave function for a harmonic oscillator usually consists of a means a normalization part, a Gaussian, and a Hermite polynomial, right?
Hermite polynomial, right.
So here we got the legendary polynomial.
Yeah, so that is because the nature of the problem. I mean, so we are just, so this is exactly not the harmonic oscillator. Okay, uh, so yeah, that is the
It is
point. That,
slightly
sorry.
means it's still a harmonic oscillator, but only shifted by a some part.
Uh,
Because in the lecture, actually,
mhm.
he got the wave function as in terms of Hermite polynomials.
Yeah, you can. Yeah, actually, these are convertible, but calling
Oh,
it precisely the harmonic oscillator, I'm not really sure that, because there are quite a few other features which are sort of, I mean, we'd never talk about in the harmonic oscillator.
okay,
Okay.
okay,
So I'll have to see the connection between Hermite and legendary actually, or Lagure.
okay, okay. Please continue.
Hmm. So this I will check. Okay. Okay. So what we're trying to understand is that, I mean, what is the physical significance, or what does the question, what does M represent? Okay. Uh, so So what we considered uh, in in solving the problem is that we was considered a symmetric gauge, so that we have a circularly symmetric wave functions, right? So these are circularly symmetric. If you can see, the Z is essentially R. You can write. So these are circularly symmetric, right? It's not, I mean, theta dependent. It's mod R dependent or mod Z equivalently. So the wave function will be circularly, I mean, symmetric. Okay. Now, in the lecture, I think I am not sure that in which. Okay, I now understand. So, can you confirm that in the lecture, which gauge we took? So, the gauge was something like this. This is Landau gauge. If that was the case, I am not sure actually. Or the gauge was something like this that we are considering. So, half minus yb plus xb 0. Which is the gauge?
Yeah, the second one only.
Oh, okay.
Not the second one. Actually, it is only minus by 00.
Oh, that's fine. That's fine. Okay, fine. Then I understand the point actually. Okay. So let me explain. Okay. So it turns out that there are three A at least. Okay. At least there are other possibilities can be. So minus YB 00. Okay. So these two are called Landau gauge, and this is called symmetric gauge. Okay. Uh, So this is the source of the, I mean, the Hermite polynomial and Laguerre polynomial or legendary. Okay. So if you take this kind of gauge, and by the way, if you take curl of any of these A, all will give you BZ cap. Okay. So there is no problem in that part. Now, these two gauges are translationally not symmetric, meaning if you take this gauge, you'll see that along one direction, the Hamiltonian was translationally symmetric, along another direction, I mean, the Hamiltonian will be not symmetric, right? So if you take this gauge, let's say, along the x direction, your Hamiltonian is not going to be translationally symmetric because you have a xb term, right? Uh, so you had a Hamiltonian which was only containing px square plus py square by 2m. Now this Hamiltonian is translationally symmetric, meaning it doesn't distinguish between x and y direction, and it is perfectly periodic, let's say. Okay. Now the moment you take this gauge and then you modify p goes p modifies as p plus ea, let's say, right? That's what we insert the magnetic field gauge. What really happens is that because of the xb term, let's say, or if I talk about the minus yb, which was taken in one of the lectures by Basu, uh, along the y direction, it will not be translationally symmetric. The reason is if you take uh, commutator with the py and h, it will not be zero actually. Okay, because
Yes,
y
yes,
and py is I h bar, right? And because
yes, right.
the momentum operators are the which generates the translation. So p are generator of translation. So that means that if a Hamiltonian doesn't commute with the I mean p operation, that means translation symmetry is broken. The moment it commutes, it is perfectly symmetric. So that was the, this is why we got the Hermite polynomial. So it turns out that the wave function is gauge dependent. Okay, it depends on the which gauge you choose. You choose Landau gauge or the symmetric gauge. The wave function can be different, but what should not be different and what is not different is the energy of the system. Okay, so
Yes,
that's
the
very
observer
important.
is the
Yeah,
same, right?
yeah. So that's why I mean the lectures we got Hermite polynomial, and in the lecture that I am continuing in the symmetric gauge. Okay, and this is why we are getting Laguerre polynomial. So this is the reason actually. You can continue in both gauges, but I choose to go with the symmetric gauge because this will have later a connection with the Corbino disk geometry, okay, which will be used in quantum Hall. I mean, in explaining quantum Hall effect. Okay. Yeah. So this is a good discussion that you came up with actually because I was just about to say that in the gauge in the Landau gauge. You usually think in terms of linear momentum, right? Whenever we are saying that translation symmetry is broken and so on, so we had in our mind that there is a linear momentum in the picture. Now, in the symmetric gauge, we have a circular symmetry in the wave function. Wave function depends only on the r, of course, with other factors into the picture, but it doesn't depend on r theta, let's say, right? If it is r theta dependent, then it is not circularly symmetric because wave function will have some value depending on the theta, right? But we only call circularly symmetric when it is theta independent, any theta, let's say. Okay, so then it is useful to think about the angular momentum in the circular geometry. So, these are the connection that we already know a little bit because once we have solved the spherical harmonics, right? There also we had a spherical symmetry and circular symmetry and so on. So from that insight, we now want to see that what happens or how do we think about the angular momentum and the connection with this circular geometry of the wave function. Okay, so angular momentum along the z direction is r cross p, which is xpy minus ypx, right? If we write the operators, or let me write simply L, it is I h bar x del del y. I'm just transforming it. I mean writing it full operator form. Now, so this is the L, I mean angular momentum operator we want to work with. Okay, and then we'll define again a lot of other algebra has to be done. We'll define this operator, partial derivative operator del del x minus I del del y. Actually, this was defined in the previous lecture also, and we define delta as this half del del x plus I del del y, and then it will be del del x. So if we use these two, del del x operator will be equivalent to del bar plus del, and then there will be another minus I del del y equal to del bar minus del. Okay, and remember we had z equal to x minus iy and z bar equal to x plus iy. Okay, so right now then we have x equal to z plus z bar, sorry, by 2, y equal to, or sorry, minus y iy equal to z minus z bar by 2. Okay. Okay, so then all of this information we already had last time. So let's see what is the L in terms of these operators. Okay, so these operators, del operators and Z. Okay, so we need to evaluate this part. So x del del y minus y del del x is nothing but, so we'll just put these things x and minus iy values. So x is z plus z bar by 2, and then what was del del y? So this was the del del y expression. So del del y will be del bar minus del by minus I, right? And then similarly, we'll just put the y and del x, z minus z bar by 2, and then minus I times del bar plus del. Okay. Okay, so if you do the algebra, I'm skipping the algebra, simply you just need to multiply each other, everything. So you will get something like this, minus z del plus z bar del bar. Okay, so this will be the final L upper, sorry. So this was this part. So then L will be I h bar x del y minus y del x. So minus h bar iota iota is minus 1, and then okay, so I'll minus z del plus z bar del bar, right? So this we can rewrite as h bar z del minus z bar del bar. Okay, so this is the L operator. Now how do we check, or how do we check that L is an I mean the significance of L in our wave function? So we just want to project, or we just want to I mean operate this operator on the wave function. Okay, so for this we'll take the zeroth wave function psi L L L, that means lowest Landau level, lowest land. So let me write full. Lowest Landau levels means n equal to 0, right? And m can be m can have lot of other values, 0, 1, 2. We do not know, right? That's what we want to find out. What is the significance of m and what are the values of m which one can take. Okay, so let me write just m. So this is the lowest Landau level, and we know that lowest Landau level's wave function was something like this. Uh, e to the power minus mod z square by 4 lb. Okay. No, it should be square. Yeah. Now let's operate this L on this lowest Landau level. So we are only using the approximate values because there will be normalization factors which we are not bothering about. So we'll operate Z del minus Z bar del bar on the Z to the power m. Again, we are ignoring, let's say LB equal to 1 unit, or we are just not writing. So LB, if we, it turns out that it's a length unit, which is root, I mean 26 nanometer by root B. So it depends on the, I mean, what is the magnetic field you have applied. I'll talk about its physical significance later on. Okay. So e to the power minus mod z square by 4lb square h bar. So what will happen is that this part operates on this, let's say. So we have z and m z to the power m minus 1, right? And then e to the power whatever it is there, this part, and plus it will operate on, so let me write, plus it will be z to the power m is constant now, and e to the power minus mod z square by 4lb square and minus z bar by 4lb square. Okay, so this acted on the e to the power term.
The second term,
Sorry,
actually, the second term will have z to the power m plus 1, right?
second term will have z to the power m plus 1. Why?
Uh, there is only z outside the del operator during the
Yeah, I
second
mean,
term.
so this part, so let's say this was z, right? So this z comes here, and then del operator is equivalent to del z.
Yes, yes. So in doing the second time, so there the z raised to m will be outside. So it will get multiplied by z and it will become z raised to m plus 1, right?
Okay, sorry. Right. So there will be extra z of this term. Right. Yeah, thank you. Right. So then I'll also do minus z bar, and then this part will be constant for this del bar operator. So z to the power m is there, and then this will operate on e to the power term. So e to the power minus mod z square by 4lb square, and then it will give me minus z 4lb square. Okay. So what do we have? Uh, so let me match z to the power m and z, and then so we have minus z bar, and then there is of course these terms, right? So and then this comes with an extra positive and negative sign. So this part and this part cancels out. Okay. So what we have is that h bar m, and then again, so this will be z to the power m, z and z to the power m minus 1, and e to the power minus mod z square by 4lb square. Okay. So okay, now we got the important thing, and this is again psi l l l m. Okay. And this was operating on psi lowest Landau level m. So this is what we got. Okay. So so what this tells us is that m, so m is really an angular momentum. Okay. For wave functions. So Landau level wave function. So what this means is that uh, if you are in a particular energy level, you can have different I mean angular momentum for the states without changing the energy. Okay, so that's what it physically means. Now so so having understood that m is literally represents the angular momentum for the electrons within a Landau level, so it remains within a single Landau level, and then so as you, yeah, any questions?
No, 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 clear.
Yeah. Okay. So what really happening is that you operate L on the psi LL, you get some M, you again operate, you get some M plus 1, and so on. So you are increasing the angular momentum without changing the energy. Okay. And this also tells us another important thing, that so the next question is, when we understood that m is really an angular momentum, the next question is where, so that means that m starts from zero, right? As you know, angular momentum can be starts from zero. So it starts from zero, it becomes one, two, three, and so on. And where it stops,
So,
that's the next
so
question.
unlike,
Yeah.
so unlike in the other cases, means other quantum cases, means problems that we have solved earlier, L
Mhm.
is quantized. So here I think it is not quantized, so we get so many degeneracies in the same level. I think that's a point to be told. Am I right?
Sorry, no, quantized, it is still quantized, right? Angular momentum cannot take any value. Angular momentum, you start from, so likewise, in you start from 0, 1, 2, 3, 4. Angular momentum also it gets from 0 to 1, 2, 3, and
Yes.
so on. But it cannot take 1.5. So everything is quantized.
Yes. Yes. Okay.
Yeah. So so what really happening is that depending on the gauge, your interpretation of the wave function and the exact form, mathematical form of the wave function changes. Okay. But these are purely theoretical understanding, right? You are just representing for your calculation convenience and so on, or the way we wanted to understand things. But physically, what is happening with the electrons, it must be at the same level for whatever mathematics you choose, right? You are in the Landau gauge or in the symmetric gauge, it doesn't matter for the electrons in reality. Okay. And these are
Yes.
different interpretation, which of course physical these are. So so the next question is, we know that m starts from 0, so that part is sorted out. M will go to from start from 0, then go to 1, 2, and so on. But where does it stop, right? I mean, it can it go to the infinity for a particular system and I mean for a particular land level. So to understand more about it and where the M actually can go and what are the sort of boundary of M, what we try to see next is that where is the peak of the wave functions. Okay, so we have wave function. So okay, so let me go to the, okay, so another important point about M is that at the I'll show some illustration in Mathematica. Let me make the comment first. At the lowest Landau level, M increases the wave function peak further and further. Okay, so we have some wave function in the Z space, right? XY plane or R plane, whatever you see, all are equivalent. And then so some there is some wave function, let's say, and there is some peak at some particular R, right? And that m is actually determines where it will peak. Okay, so suppose m equal to 0, then it will peak at, let's say, r equal to 0. M equal to 1, then it will peak at some r value, okay, in the xy plane. And m equal to 2, this again r will be something different, and so on. So how do we determine the peak of a wave function? The peak of a determine I mean wave function, to determine, we will take del r of mod psi LLL m square to be 0, right? At the peak, it should be 0 because the slope is constant here. Slope is 0 basically. So if we do that, so what we have is that, sorry, this is disturbing. Yeah. So what we have is r to the power 2m by LB to the power 2m, I think. Yeah. To the power minus r square by 2LB. So what we have done is that Z mod Z is r. Okay, or rather, so I think, let me see. So we had Z to the power m. Oh no, okay. So that is fine actually. Yeah. So what we have is that del r of r square, let's say. So Z is equivalent to r we are using, right? So this we had 4 LB square, I think. Uh, simple LB to the power m. So this is the expression I'm using. This one. So LB to the power m e to the power minus mod z square means r square by 4 LB square and then whole square, right? So this part is psi LLL m and then whole square. This equal to 0. So that is what we want to, I mean, this is the condition. Okay, so that means we will have del r of r to the power 2m throughout this LB constant values e to the power minus r square by, it was 4 LB square, it will be 2 LB square, right? It is 0. Now let's determine this. So this operates on r to the power 2m. So 2m r to the power 2m minus 1 by okay, let me write, I mean, keep the LB to the power 2m actually. Okay, LB to the power 2m. So LB to the power 2m e to the power minus r square by 2LB square minus r to the power 2m by LB 2m. Now this part. So what we have is that minus 2r by uh, 2LB square and then e to the power minus r square by 2LB square, right? So this will be equal to 0. Okay. So what are the things we can take common? R to the power 2m minus 1 we can take common from these two terms. So R to the power 2m minus 1 and then LB to the power 2m. So LB to the power 2m and the whole exponential term R square by 2LB square, right? So we have 2m minus uh, so have I missed some minus somewhere? Okay, so this will be plus actually. So this minus of minus 2, so R by LB square. Yeah, so that is it, I think. Okay, so another R here. So I have, so this R by R to the power 2m we will write as 2m minus 1 into R, right? So I'll take R to the power 2m minus 1 common. So this R goes here. So we'll have only R square. Okay. Uh, yeah, fine. And this will be equal to 0. So this part cannot be 0. If it is 0, then the whole wave function itself will be 0. So this cannot be 0. So this part is 0. So what this gives me is that 2m equal to r square by lb square. Okay. And this means that r equal to root over of 2m lb, right? So this is an important result. So there are two things we have observed. Okay, so M represents the M is actually an angular momentum for the wave functions. That is number one. Number two is that, so remember that this R is the peak value of it, right? Peak value of the wave function. So the peak R or R peak at which the wave function peaks, wave function value peaks, is also proportional to root M. Right? So as if my m increases, the wave function peak also spreads out. Okay, so that means if m increases, wave function peak spreads out. Okay, okay. So these are the two important things, and then third important thing is that this also sets a boundary, right, on the value of m, because what is r? So we have a sample like this, let's say. So this is along the x direction, this is along the y direction, let's say. So what is the value of r? R will be somewhere else. So let's imagine this is my origin, right? So r will be some value here. Let's say here it is 1r, and then it can be r here. This is r here, but it cannot be this. If my sample is itself within bounded within this particular boundary, then this R is not allowed. So if this R is not, what this will physically mean is that my wave function is peaked somewhere here, let's say, or wave function have spread out with outside the sample, but that is not possible. I mean, it can have tunneling in the quantum function, I mean, wave function. It can have spread out within the boundary, I mean, around the boundary, but it cannot be here. So this implies that my m value is also restricted by the values of r. So let's say r, so let's say this is the maximum value of r I can go, right? So this is the maximum value. So r max. So corresponding to R max, I will set the 2m LB, and this is also not only a dependent function of the sample size. So this is dependent on the sample size, and this is also dependent on the magnetic field, right? So m value is of the order of, let's say, so let me write, sorry, m is of the order of R max root of by LB square. Okay, so this will be R square and LB to the power 4. No, sorry, what is happening? I messed it up. Yeah, so this will not be R LB square. So this is simply LB. Okay. So this will be LB square. So this will be R max square by or so LB was root over H bar by EB. Okay. So that means LB square will be a H bar and then EB on top of it. So if I just write the, I mean, free parameters, so we have R max square B. Okay. So this sets you the rough uh, boundary of M. So M started from 0 and 1 and 2 and so on, and where it can go maximum, it is determined by the sample size that we have and as well as the amount of magnetic field that we are applying. Okay, so these two things determine the what will be my maximum M. So again, just to remind, so we had n equal to 0 state, n equal to 1 state, and n equal to 2 state, and so on. And there can be many particle within the n equal to 0. So there will be many value of m. Okay, so m equal to, so these are values of m, let's say. And so these are many values of m, and depending on the sample size as well as the magnetic field that we apply, it will have how many m values, whereas m max will be this one. Okay, so these are order of estimates. These are not precisely it is the, because there are factor of e, h bar, 2 and so on. And it turns out that this number of m values starting from 0, it can be huge actually. Okay, for a simple micrometer size of sample. So each landau level are hugely degenerate, meaning it will have a huge number of wave function which all will have the same energy. Okay, this or this or this. So I hope the significance of m is now much more clear. Now let's try to see this wave function, how they look like. So wave function, by wave function I mean, so the general wave function would be somewhere I wrote, yeah, so this is the general wave function. Okay, so this is the general wave function for general n and m. Okay. Okay. So if you have any question, please ask.
No, no.
Okay. So what I'll do is that I'll just try to show what is happening with the different wave function and what we have said here. Does that numerically we do get all of those things or not? Okay. So I just need to stop sharing, I think. So how do I do that? Okay. So just share. Uh, can you see my screen?
Yes.
Uh, okay, okay, fine. So what I have done is that so I have just I just written some. Mathematical code to plot, and these are actually also internet available. So the name of this is Landau levels in a magnetic field. So the exact code is not available. I have modified what I wanted to say, depending on our problems, but this part of the code is actually available in public domain. Okay, so if you see that we have a e to the power, I mean x square by y square by 4 and LB square. So I took E and H bar to be 1. Okay, you see that there is magnetic field also. Okay, let me, uh, how do I zoom out? Not sure. Okay, yeah. Okay, yeah. So, so if you see, this is the e to the exponential part, and then this is the r square of m part, right? X square by y square, and then you can remove these two factors and so on. This is the Laguerre, right? Laguerre polynomial. It has two indices, n and m, and of course it also depends on the r magnetic field value. We took some value of x and y, which will set the maximum r, and the trivial things that we need to do. Okay. So if we run this, so this is I need to zoom. Okay. Still big. Yeah. So so this is what the plots. So this is n equal to 0. Okay, n equal to 0 and m equal to 0. So you will see that these are n and m you can change. Okay, and this is the real part of the wave function. So okay, this is not true. I am not plotting the real part of the wave function actually. What I am plotting is that the density. So I have taken the square actually. So if you see, so so this whole part is the wave function, and then I have taken the square of it. Okay, so here is the square. So I should have changed the title of it, but anyway. So if you see, so these are my, this is let's say x axis, and this is let's say y axis, and this is the z axis is the wave function. Okay, so everywhere it is 0, let's say, and then at exactly 0 you are seeing the peak. Remember, this is for 0th Landau level. As long as you are in the n equal to 0, so we have a 0th Landau level, and m equal to 0 means we have a angular momentum of 0. Okay, in units of h bar. Now let's increase the angular momentum by 1 unit, h bar unit. You see that what you see is it is becoming 0, and then maximum at some other point. Okay, so so this is becoming 0 at 0, and then maximum at at some other values of m. Okay, uh, so how do we understand this? This we understand because whenever you have m to be non-zero, so this part of the m to be non-zero at x and y. So whenever you had m equal to 0, right? So if you have m equal to 0, then whatever your x and y will be, so the maximum peak will occur at the origin, because this part will be 1 then. But whenever you have m not equal to 0, 1 or something, then this part will be finite. Instead of being 1, and this part will be finite. And that will make the maximum of the wave function to be picked at somewhere else. Okay, so I'll go to the, iPad, and then I'll explain more mathematically. But let me show what is really happening. Uh, so how the things are spread out. So for this, we'll go to the density plot, let's say. So let's say, so this was my n equal to m equal to 0. Everywhere it is 0, and then it is peaked exactly at the, 0 point, right? If you increase the m at the 0 point, your wave function is not maximum. Rather, it is maximum at somewhere else. It is not at the origin, at least. That is clear. You go to m equal to 2, again wave function further spreads out. Wave function is not maximum at 0, but it is farther away from the origin. You increase further away from the origin, increase by another value 4, again further away from the origin. Okay, I have included more actually. I may include more 5 and 4, but what you already see is that after certain point, after certain magnetic, m value, this peak. So this is the peak of the wave function. Okay, so this is where the wave function get maximized. So this will be seen in the 3D plot better. So yeah, so this is the maximum you see. This is, let's say, 60 value. Okay, so this keep go increasing, but as I've argued that it cannot go beyond a certain point, it cannot go beyond sample size. So that sets the boundary for m. Okay, so this was the story for within the Landau level. As you increase the m value, your wave function peak spreads out. Okay, and this is just same thing I am saying again and again. So n equal to 0, m equal to 0, you have a peak at so this is the radial part of the wave function. So you have a peak at 0, and then you have a, I mean, m equal to 1, you have a peak at somewhere else, m equal to 2, further away from r, I mean from origin, 3, again further away, 4, again further away. Okay, and this goes on. Okay, and these are our energy levels representation, let's say. So this is not uh, no, it is not showing correct thing actually. But anyway, so the idea is clear. So n equal for n equal to 1. So this is how the things looks like. Let me go to the density plot. This will be better. So for the for so n equal to 1, what really happens is that you get another peak, right? So so you for n equal to 0, m equal to 0. Let's start with this. So for n equal to 1, m equal to 0, your wave function peaks at the origin. Okay, but it also peaks out away from the origin. And remember, we said that our wave functions are circular. You see the circular wave function here also. Now, if we increase the n equal to 2, what you see, n equal to 2 and m equal to 0, what you see is that again, as long as you are m equal to 0 for any Landau levels, n equal to 0, 1, 2, 3, 4, your wave function have maximum value at the origin, and then there can be other peaks as well. So if you see that apart from this 0, for n equal to 2, you will have another 2 peaks, right? Apart from the origin. If you do n equal to 1, you see that there is one more peak beyond origin. If you put n equal to 3, what you see is that you have a peak at origin as usual, but then there is 3 other peaks, okay, surrounding the origin. So that's what the I mean interpretation in terms of wave function, what n and what m does. Okay, so once you are fixed n, as you increase the m, your wave function peak spreads out. Okay, the number of lobe remains same as long as you are having fixed n, but your wave function spreads out. Okay, so is this thing clear?
Yes,
Okay,
yes.
okay, so let me stop sharing this, and yeah. Yeah, so so that is the physical picture of m that we're trying to find it out. So yeah, so this actually completes the discussion on, I mean, the Landau levels for at least 2D free electron gas, and the number of degeneracies we can find out by, so how many number of states in a within a, let's say, within a single Landau level will have. Let's say imagine a circular wave function, sorry, circular geometry. Okay, so these are just estimate. That's why we can take any geometry, and the number of degeneracy factor. Okay, will be, let's say I have, so this to be r, so this is the size of the sample, so pi r square, okay, by 2 pi lb square. Or actually we already did this actually, so let me not repeat. Yeah, so this was the relation. Okay, so next we want to understand the I mean so this was the picture for 2D free electron gas. So the story was we had a something like this, right? Where this was the energy was simply h bar square k square by 2m. This was k direction, and once we applied magnetic field, so this was magnetic field equal to 0, and this is magnetic field not equal to 0. What we got was this. So n equal to 0, n equal to 1, n equal to 2, 3, and so on. Okay. So what is really happening? Initially, I had this wave function. Wherever your Fermi energy lies, it doesn't matter. uh, if your Fermi energy lies here, then it's a metallic system, right? Because the all over there is a states, there is no band gap in the system, so you are in the metallic regime. But as long the moment you apply sufficiently high magnetic field, you are depending on where you are. I mean, where is the Fermi energy? You can be in the insulating regime. So suppose you have Fermi energy here, right? That means there is a band gap of this, right, between the two bands. So these are Landau bands. So you are essentially in the insulating regime. Now, if you have Fermi energy exactly somewhere in the Landau level itself, somewhere here, then you can have conduction because there is a band, and then the electrons can conduct electricity. Okay, and this we will see more in the upcoming quantum hall lectures. So what we'll observe or what we'll explain is essentially what we have studied in first three lectures, that in the topological insulator, although band structure wise it is in the insulating state, but they can conduct Hall current, right? And this quantum Hall response is also the exactly similar thing, that we are in the insulating regime, but yet we will have some Hall voltage. Okay. So yeah, so we can do in terms of the, I mean, 2D free electron gas. That is where the first quantum Hall was observed in 1982. But so just to give a modern perspective, I wanted to do the graphene picture. Okay, so the quantum Hall effect in graphene. The physics of both the, I mean, graphene and the 2D electron gas are essentially same, but the degeneracy structure of the uh, uh, quantum Hall. By degenerate structure, what I mean is that in quantum Hall, what you will see is that we have this kind of figure, right? Where these are the, I mean, the Rxy versus magnetic field, and Rxy is essentially 1 by nu h by e, no, the opposite, h by e square. Okay, and these are nu are the, I mean, the each plateau, and this nu are different for, so let me write different for actually 2D electron gas and graphene. Okay, so I think in the lectures what I mean, what is covered, 2D electron gas or graphene?
In lectures, first it started with the 2D electron gas, and later graphene was discussed. First,
uh,
the graphene was discussed in a way where first it was in a general discussion.
mhm.
So he said that intrinsically graphene doesn't has any means these whole features, but when we break the time reversal symmetry, then because he's going in a fashion that we have to make what are the ways to make a graphene topological. In that sense, he is taking. First, he start with 2D electron
Mhm,
gas.
mhm.
After that, he goes to graphene, and he says that intrinsically graphene doesn't has any topology. So we are trying to find ways to get topology by breaking the symmetry. in that way.
Okay, so that will be the quantum anomalous Hall response. But in graphene, likewise in the 2D electron gas, if you apply sufficiently high magnetic field, it's a quantum Hall effect can be shown actually. Okay.
Actually, in graphene, he hasn't discussed about magnetic field effect,
All
only
right. Okay.
liquid
Okay.
magnet.
Mhm, mhm. Okay, yeah. So the okay, then it is fine that we'll study in the context of graphene because that's where the most of the experiments right now are happening, and also the Landau labels are a bit more subtle in graphene than 2D electron gas that we have studied. Okay, so
Okay.
I'll try to cover a little bit of Landau level structure and what is I just wanted to highlight that what is the difference between uh, graphene's Landau level and two-dimensional electron gas Landau level. Okay, okay. So let me start that part. Okay. So graphene, as you know, I mean, just to be very brief here. So okay, so there are two types of atom. One is A type of atom and another one is B type of atom, right? And around these two valleys, sorry, if you convert it in the Brillouin zone, the Brillouin zone looks like again similar, and these are called K points and K prime points, and around this K point and K prime point. So actually, graphene will have something like this band structure. Dirac point, and then somewhere here there will be almost flat like band and then something like this. Okay, this doesn't look good, but something something like this. Okay, so this is the energy, this is, let's say, K. So there are different points in the Brillouin zone. So this is, let's say, K point. So this is, let's say, K point and then K prime point, and this is, let's say, the let me write it. Okay. Uh, so this is K prime. Now, if we perpendicular to this, okay. So this midpoint is M between the K and K prime, and this is the gamma prime. Sorry, gamma point. Okay. So these are nomenclature that we use. So this energy has been plotted along a certain direction, right? So what we have plotted is that so we started from gamma, went to K, and then went to, sorry, what is happening, so we started from gamma, we went to K, and then went to M, and then come back to gamma. Okay, we could have gone to K prime also, but we're not doing here. So this is the gamma point, and this is the K point, Dirac point. So somewhere here, if you zoom out, it will be Dirac like point. So something like this, and this is the M point. Okay, where at some point you will have no slope. So del epsilon del K will be 0. This is a exact point. This is exaggerated, but it's a point actually. And here you are again coming back to gamma. So this is a particular path we have chosen starting from gamma to K, M, and then gamma. Okay, and most of the low energy physics that happens, so this is, let's say, 0. Okay, and this is energy is in the EV range. Okay, and most of the experiment that happens, transport experiment that happens within this region. Okay, and this will be few MeV actually, maybe 50 MeV. Okay, so within the 50 MeV range you do the transport. So that means that you are really not bothered about this particular set of bands or set of energies. Rather, we are focused on here. And here you can actually very accurately represent the band structure of this part as simply linear band structure, right? H equal to H bar Vf sigma dot k, where sigma is only sigma x, sorry, sigma y vector. Okay. So this Hamiltonian is written in the A and B sublattice as in the, I mean, I think the lecture will clear all these things. A and B sublattice. So if you write in terms of 2D, I mean, matrix format, you will have something like this: 0, H bar Vf, uh, Kx minus I Ky, Kx plus I Ky, 0, right? And VF is associated with something like root 3 by 2 T. Yeah, that's it, I think. Or maybe it is also associated with A. But nonetheless, so VF is proportional to the hopping parameter T. Sometimes we also call it gamma 0, but it is essentially same thing. Now, so these are written in the A and B sublattice. So this is A sublattice and then this is B sublattice. And actually it is written in the PZ orbitals of A sublattice and B sublattice. Okay. Okay. Now, if we quantize this Hamiltonian, right? So this is what the Hamiltonian we have. Now, if we apply magnetic field not equal to 0, then again we will construct the pi operators, right? So this is the operator that we will take, and again we can again we can construct the A and A dagger operator, raising and lowering operator. So it will be root over 2e b h bar. So this has been done in earlier lectures, pi x minus I pi y. So this will be A operator and then 2e b h bar, A dagger operator. Okay. I'm just going over it, but I wanted to cover the key important point that I need to tell. Okay. So if we use these definitions and this definition, then your Hamiltonian will be uh, root over 2e h bar b, uh, 0 a dagger 0. Okay. So this is a 2 by 2 Hamiltonian in the A and B sublattice basis. Again the same thing we'll do. So A dagger of acting on n root gives me n plus 1, n plus 1 state. I'm not writing, ignoring the or not writing the explicit m index. Okay. Angular momentum index m. Ideally I should always write n comma m. So this is the complete state, but not writing m because energy doesn't depend on m. So a n equal to root over of n minus 1. So this is known equation. Now what we will see is we want to see the energy, right? So remember that two-dimensional electron gas have energy epsilon n to be n plus half h bar omega c. Okay. Okay. So what we have, uh, let's see if I'm missing any factors. No. Okay. So we are not missing any factor, but I am also not bothered about the some factor. I just want to see the shape of the Landau level energy actually. Okay. Okay. So given that we have this Hamiltonian, And we know that a dagger will I mean operating on n will lead to n plus 1th state. So we take this answers of the form of for the form of the wave function. Okay, that wave functions looks like this. It will be a two component wave function n1 n2, right? So n1 corresponds to the a sublattice and n2 corresponds to the b sublattice. Okay, so what we want to operate is that h bar is essentially proportional to 0 a dagger 0, right? So this is what we found here, this part. Okay, now how do we find energy? You operate, let's say, so this, I call it psi. Okay, uh, psi acting on energy, it will give me again psi, and we want to find energy equal to what? Okay, so what we have is 0 a dagger, 0 n on, n2 epsilon n on, n2. Okay, okay, so from this equation, what we can see is that if you do the matrix multiplication n on, so this part goes acting on this will give me 0, right? Plus a operating on the n2, so this will be n2. Then so what will give me is that if we compare this right hand side, this will give me epsilon n1, right? And so let me erase this part, and then similarly you will have a dagger n on, this will be equal to epsilon of n2, right? So this acting on this part and giving rise to this. Okay, so from this two equation, what we can infer is that n2 equal to must be equal to n1 plus 1. Okay, why? From both of these equation it is the same thing. So what a does is that a decreases the state by 1, right? So that's what we have seen here. So a is the annihilation operator. So a acting on n, it decreases the state to its lower energy, lowest, I mean its immediate lower energy, n minus 1. So that means that a n2, so this n2 must be equal to n1 plus 1, right? From this expression as well. What a dagger does, a dagger acting on n1 raises the it to its immediate so immediate higher energy level. So n1, so n1 acting on a dagger, it raises to n2. Okay, so that means that n2 equal to n1 plus n1. Sorry, n2 equal to n1 plus 1. So let me pictorially present. So suppose you have a n2 state. Okay, so this is, let's say, n2, and this is, let's say, n1. Okay, so the moment you operate this a dagger to n2, it brings you here annihilation, so n1, and the moment you operate a dagger to n1, so this is my n1 state, it goes here, right? N2. So that means that we have n2 equal to n1 plus 1. So now our wave function becomes, we took initially as n1, n2, but after this condition, imposing this condition, what we have is, let's say represent n1 as n, some n, right? And n2 is always n1 plus n, so that means n plus 1, right? So this is my actual wave function. Okay, Or you can equivalently take, this is also you can take that I will take n minus 1 n. It doesn't matter. It is the same thing basically because n can n we are not specifying starting from 0 to 1 and so on. Okay. Okay. So these things are by the way valid for n not equal to 0. Okay. For n equal to 0 there is a subtle case and that's what I want to highlight. Okay. So these are all true for n not equal to 0. Now once you know this, okay, what you can find is that so your Hamiltonian, if you take everything into account, we can find that your Hamiltonian, the exact p factor will be h bar Vf by Lb. Okay, sorry, L not Lb square. H bar Vf by Lb, and then this will be 0 a dagger 0. Okay. Now if we solve the equation, let's say root over 2 h bar Vf by Lb and then 0 a dagger 0 and then you operate on n plus 1 epsilon n n plus 1. So this will get two function, right? Two equation. Now once you solve these two equation, let me actually solve one part at least. So this 0 and n, it is 0 plus a operating on n plus 1, then equal to epsilon, it will be n, right? So what we'll have is root 2 h bar Vf by Lb, and then a operating on n plus 1, we know that it will be n and sorry, right? Epsilon n. Now from this, what we get? So this is common. So epsilon, which is n dependent, energy, Landau level energy n dependent, which is given by h bar Vf by Lb root of 2n. Okay. Now, if we put everything together, I mean LB, remember that it was h bar by EB. What we'll find is that epsilon n 2n h bar square uh, omega c square. Now we use new definition of omega c, which is Vf by Lb. Okay. Now, if we write more explicitly, epsilon n equal to 2n h bar square Vf square by h bar square Eb. Sorry, this will be simply h bar. So then epsilon n will be 2n h bar Vf square Eb. Okay, and this is the most important thing that okay. So this root over should extend here. So similarly, you will also get the negative also. Okay, so here I have only got positive, but you can also get the negative. Two equation, 2 by 2 equation, so you will get positive and negative, both positive and negative, right? That's something we know. Uh, so the important point is there are quite a few important points. So one is contrast this with the 2 DEG case. So this is sorry. So this is two-dimensional electron gas case, and this is graphene case. Okay. So for two-dimensional electron gas, we had n equal to 0, n equal to 1, n equal to 2, n equal to 3, right? And our energy was n plus half h bar omega c. Okay, so here omega c means sorry, EB by m. Okay, remember that for the two cases I am using different notation of this is m. Notation of omega c because it's popular in the literature. Okay, and the difference between two consecutive energy levels was always h bar omega c, right? That is number one. Number two, the energy linearly increases with the magnetic field. So let me show this. So these are, let's say, epsilon n, and these are, let's say, b. Okay. Am I right? Yeah, fine. So so let's say this is some energy, right? At b equal to 0, our energy is 0. Okay. So this is, let's say, n equal to 0 level. And again, for any n at b equal to 0, energy is 0. But then for b equal to some finite, n equal to 1, we'll have higher energy. So this is 1. And this is, let's say, n equal to 2, and so on, right? So that's how the 2dg case, in the 2dg case, energy was increasing linearly. The more you increase the magnetic field, the more energy increases. It's directly proportional. Now let's see what happens for the graphene case. Okay, so now let's draw the energy levels. I'll come back to the n not equal to 0, sorry, n equal to 0 case. For now, I am only plotting n equal to 1 case, okay? Rather, I'll have both positive and negative. So let's say this is n equal to 1, n equal to 1, minus 1. So n equal to 1, n equal to minus 1. And then something strange happens, n equal to minus 2. Um Sorry. Okay. I'll cover the n equal to 0 case. That's an exceptional, I mean, important case. And don't confuse that n can be, how can n be negative, right? So here n is within the root. So this plus minus I am representing by epsilon n. People also write as something like this. Sine function, signum function is it's called, root over of 2n h bar vf square eb. Okay, where n can always be finite, but this is just to represent people sometimes, just for convenience, people call it n equal to minus 1 and minus 2. But that's not so. And then they write as like something like this, mod n. Okay. So this is the mod. So that n can be negative, but then energy is essentially fine. Within the root, it is always positive. Okay. Just a way of representation. Uh, so what really happens, what I wanted to show you is that the difference between two consecutive Landau levels. So before that, let me write h bar omega c is here Vf by Lb. Okay. The difference between two consecutive Landau levels decreases as we go to the higher and higher Landau levels. Okay. And that is because, let me write somewhere here. So epsilon n plus 1 minus epsilon n was, in this case, will be root over of n plus 1, right? Minus root over of n, and then something. So this is, let's say, proportional. This is proportional, and then root b. Of course, there are other h bar and so on and so forth. That's a constant. And for this case, epsilon n plus 1 minus epsilon n was exactly, so what will be it? So n plus half minus n, sorry, n plus 3 by 2, epsilon plus 1, n plus 1, and n plus half. H bar omega c is common. So H bar omega c means we will only have B, right? For for this omega c. So this means that n cancels out, and then you will only have 3 by 2 minus half means 1. And let me put it proportional, propor proportional to. So epsilon n plus 1 minus epsilon n is proportional to B. Okay. And this doesn't depend on the n. So you take any two consecutive Landau levels, as I have shown here, this or this or this and this doesn't matter. Everyone have the same difference between the two consecutive Landau levels, right? But this is not the case for graphene. You see that if you just think about this particular function or do some calculation, right? It not only increases or varies with the root b, as the energy was also varying with root b, But also this function, you can actually observe that as the n increases, this function also get decreases, the difference between this function, these two. Okay, so let me write. So as n increases, epsilon n plus 1 minus epsilon n decrease, and that's what I have tried to show here. Okay, so this was a difference between n equal to -1 and -2. It has a this much of difference, but then n equal to -2 and -3, this will have less difference than this. Okay, so again same thing happens. Okay, this is +1 actually. So this is what happens for the graphene and 2DG. Okay, and then now let's come to the case of n equal to 0. Okay, what happens for the n equal to 0 case? So if is everything clear? Okay, so okay, I just missed one thing. So I needed to plot epsilon versus b. So we have so far n equal to 1 minus 1. So this varies with the root b, right? So this is, let's say, n equal to 1, n equal to 2, n equal to -1, n equal to -2. Okay, and so on. So yeah, so these are the main contrast between the two-dimensional electron gas and graphene Landau labels. And there is one more n equal to 0 case. I'll do that now. So if you have any question at this point, please ask.
No, no, no problem.
Okay, okay, okay. So we have seen what is the difference between two-dimensional electron gas and graphene's Landau labels. In terms of how the magnetic field, how the energy basically depends on the magnetic field, the contrast between these two cases, and then also the difference in energy between the two consecutive Landau levels. In both aspects, they differ significantly, right? Qualitatively, of course, they differ. And then one more important point is what is the curious case of n equal to 0. Okay, okay. So let's see for the case of n equal to 0. Yeah, okay. So the reason is, so n equal to 0 lambda level. So the reason we the same thing, same wave function that we are considering. So we consider this wave function, right? For n not equal to 0 lambda levels. So n plus 1. Now the reason is this doesn't work is that our Hamiltonian has this kind of form. Okay, so this is, let's say, 0 a dagger a, sorry, 0, right? Now if you operate this, if you operate this on psi, so h psi essentially means that you'll have 0 a dagger 0. Now let's particularly focus on what happens to the 0 case, right? N equal to 0. So this is, let's say, 0, and this is, let's say, 1, right? For n equal to 0. uh yeah, so am I correct? Yeah, that's fine. Yeah, so this is what we have. This wave function I have just used it. Okay, okay. So this doesn't create any problem. Why? Because you just, if you operate this, if you solve this matrix product, what happens is that this operates on this. It is 0. A operates on 1, right? Operates on 1, gives me 1 root over 1 of 0 state, which is fine. This is I mean, lowering operator, so it decreases the one state to its lower state, 0. Similarly, a dagger operates on 0, so this operates on 0, right? And then it raises the state, root over 1, meaning 0 plus 1, 1, right? Which is also fine. But what is problematic is that uh, yeah, so I just missed to point out one thing. So this, yeah, okay. Yeah, so it's fine. So I'll point out. So if you solve this equation, so this part, right? So let me solve it again for this 0 1 case, okay? Then it will be clear. So I have this equation, and then I had epsilon of n, or let me write it epsilon 0 1, right? So so to essentially have is simply these two set of equation. A acting on 1, it will give me 0 state equal to epsilon 0, right? But then A dagger operating on 0 will give me 1 state epsilon 1, right? So these two equation will give me. Now, what is the problem here? The problem is this was root over 1, because remember that this part actually comes from uh, this A dagger operating on 1. This gives me this, okay? And use a different color. A dagger operating on 0 gives me this, okay? Now we are searching for the lowest Landau level. So level n equal to 0 with energy epsilon equal to 0, right? So but what we are getting from here is not the 0 energy level. So it has the energy equal to 1. Of course, it has a units of h bar omega c and so on, which I have not written. So this was some factor, okay. But this tells us, this particular calculation tells us that energy for the zeroth state is 1, which is not 0. But we have seen for the two-dimensional electron gas as well, and this is from the basic structure of I mean the raising and lowering operator and so on, that there will be a zero energy state at no, with the energy 0, right? And that is the difference between classical and quantum pictures, okay? But this is what we are not getting. So that means that 0 1 is not giving me actual 0 energy or lowest energy, both are equivalent to say 0 energy or lowest energy state, okay? So this is what the problem is. We wanted to find the lowest energy or the ground state energy with the energy being exactly 0, but we are getting from this equation that the energy have 1, of course, in units, again in units of something. So this is not the true ground state of the system. This is not representing the true 0 energy Landau level. So what about this? So what about this for 0th energy Landau level? So what we'll try out is that 0 and n equal to 0. So here I am writing n equal to 0 because this 0 is actually 0. It's not a 0 state. Okay. This is not 0 state. It is just a null. So if we try this, we have a Hamiltonian structure something like this: a dagger 0 acting on null and n equal to 0. So this is the ground state, and let's see what happens to our energy. Uh, so yeah, now if we do calculation, so what really happens is that this operates on this, right? So a n equal to 0 gives me epsilon 0, epsilon times 0, okay, epsilon times 0, yeah, no, yeah, and then a dagger operating on 0, or this is just 0, equal to uh, so plus 0 into n equal to 0 is giving me n equal to 0. Okay, so these are the two equations. So I should have written here 0 plus 0 times n equal to 0 state equal to epsilon n equal to 0. Okay, okay. Okay, so this is what is trying to say that uh, so yeah, so if we write this as, so this will be 0 plus 0 equal to epsilon n equal to 0. Remember, n equal to 0 cannot be 0 because we have a I mean n equal to 0 is a state, right? It has a e to the power minus mod z square 4lb square and so on. That's we have seen earlier. Okay, so so what this expression necessarily means is that epsilon itself is 0, right? N equal to 0 is a state, say state which is not, which is finite. Okay, finite. So that means that epsilon equal to 0. So what this necessary, and this is also evident from this also, this particular part also, that destructive operator operating on the zeroth state, on the ground state, will give you null. This is something basics what we have learned in while we are solving the again harmonic oscillator case. So both the condition satisfies, right? So this means that 0 n equal to 0, sorry, is the for the lowest odd zeroth uh, level of graphing. Is this thing clear? This is actually important. Yeah. So if you do not, let me know if there is any confusion.
Yes, yes, clear.
Okay. Okay. So what is important is to note that we are writing Hamiltonian. So let me use different colors. So we are writing Hamiltonian of this form. So here there are 0, 0, and there are some operator, right, in the A and B sublattice, right? And this wave function of this zeroth Landau level, so psi 0 lowest Landau level, let's say, in same notation, what we are having is a 0 n equal to 0. Okay. So, and this is also AB basis, right? So what this means is that zeroth Landau level, uh, what should I write? Or zeroth Landau level wave function, because this is essentially wave function, lives on the, so I hope this is clear. So what we are finding is that the wave function form has to be such that the component corresponding to a sublattice is null. It is not a zero state. Okay, simply zero. Whereas the component of the wave function corresponding to the lowest Landau level for the B sublattice part or the component is the actual, I mean, lowest energy state. Okay, n equal to zero state. So this implies that zeroth Landau level wave function, which is this one, lives on the B sublattice. Okay, so this is the physically important point that one is to remember. And on top of this, remember that it has two values, right? What we are solving for, what we are solving for when we started solving this expression or this Hamiltonian is, let's say, for the value xi equal to 1 or the k value actually. Okay, so this is what we started with. So let's say k value. Okay, and for k prime value, so the Hamiltonian, so now let me write k prime value. So for k prime value, Hamiltonian is again the same h bar Vf. This is at b equal to 0. Uh, what happens is that sigma dot, now the things becomes, so let me write the general Hamiltonian. Xi is the value index. Okay, xi equal to plus 1 means k value. I hope these were covered in the lectures, right? Xi equal to plus 1 and minus 1 or k prime value and so on. So h bar Vf xi, uh, kx sigma x plus ky sigma y. Okay, so this is the full Hamiltonian of both the k and k prime value. If you put xi equal to plus 1, you will get k value. If xi equal to minus 1, you will get k prime value. Now for k value, what we got when we quantize the Hamiltonian, I mean the we converted k to pi, right? Pi means h bar k or h bar k plus Ea in presence of magnetic field. So k and b not equal to 0. So we had this kind of structure, a dagger 0, right? So Hamiltonian of k, let's say. Now, similarly, for k prime and b not equal to 0, I am not solving the full, I mean, I am just writing. For k prime, but we will find that the operator forms will be a dagger a, 0. Okay. And why this flip in the a and a dagger? Remember that a and a dagger has a different sign, right? So pi plus I pi y, I think, or I might be, I mean, just flipping the sign. Let me check. A dagger was pi x minus I pi y. No, E dagger was pi x plus I pi y, right? Pi x plus I pi y and pi x minus I pi y. Now, why this flip happens? So if you see this one was A and now it is becoming A dagger and then A dagger and A. Of course, this will come with an extra overall negative sign and so on. All of that is fine. We're not, so I should not write equal to. So these are just proportional. Okay. This you can understand because for xi equal to minus 1, there will be an extra negative sign here, right? So this there is extra negative sign here. And once you incorporate that, you will get that the negative sign carried by here and here will carry forward, which will give me extra negative sign in front of the whole Hamiltonian, and then this will be flipped. Okay. Now, for n not equal to zero lambda levels, so n equal not equal to zero lambda levels are similar as k value, except the fact that except now you need to work with wave function. So remember this we are at n equal to 0 of the form of just flip the the way we wrote it. Okay, so initially we had this n plus 1. Okay, you just write something like this. Sorry. So what you write is that n of so initially this one was bigger n plus 1. So this one must be bigger now n plus 1. Okay, so you just flip the n plus 1 and n state and you will get the same energy. And you need to do this because the operators also got flipped, right? So if you compare this. Now, similarly, n equal to 0 lambda level also you need to do the similar thing. N equal to, sorry. So to find the n equal to 0 state for the sublattice, two sublattice, I mean k prime sublattice, n equal to 0, the valid wave function, lowest lambda level, will be something like n equal to 0 state, this is state, and this is null. And let me try k prime and contrast this with psi ll k, which was 0 n equal to 0. And this is expected because your operator also got flipped, right? A and A dagger operator got flipped. So we saw that here uh, lowest lambda level wave function, I'm writing in short, wave function lives in B sublattice, right? Here what you see is that lowest lambda level wave function lives in A sublattice. Okay, so these are the two important point that I was trying to make. Now so yeah, these are the all the differences that we have. So if we summarize this, so for Dirac like or the graphene like, so initially we had something like this, right? So initially around the k prime and k point, so let's say let me draw. And k prime so these are, let's say the backgrounds are, let's say b equal to 0, right? You are having exactly linear dispersion. Now once we apply magnetic field, you have a zero energy state. Okay, and then you have n equal to 1 state somewhere here. Let me put zero energy exactly there. No, so I have to put here actually. So here itself, okay, at exactly crossing point. So because this is the general energy, and you had n equal to 1 state. So this was n equal to 1 state, this was n equal to 0 state, this was n equal to minus 1 state. And as you increase the n, remember that the lambda level, the difference is going to decrease slowly. That's what we have seen, right? N equal to minus 2, n equal to 3 will be even more closer, let's say n equal to minus 3. So this is n equal to minus 3 and so on, right? And same structure gets repeated here. So we have a n equal to 0 state, n equal to 1 state, let's say here, and maybe here n equal to minus 1 state, n equal to 2 state will be closer, minus 2 n equal to 3 is even closer. Okay, now here is the distinct point. So this is, let's say, k prime value, this is, let's say, k value. For k prime value, so this particular part, different colors, yeah. So for k prime value, it lives on the b sublattice, or no, a sublattice. Okay, and for k value, it lives on the b sublattice. Okay, so these are the crucial difference between the between the of the Landau levels between two consecutive sublattices. Okay, so every higher Landau level structure is same, n equal to not equal to 0, but n equal to 0 Landau levels, there are two energy levels for n equal to 0. The degeneracy is 2 for the n equal to 0 Landau levels, and those two corresponding to wave function lives on in one valley it lives on the a sublattice, in another valley it lives on the b sublattice. Okay, yeah, so that's the difference. So is there any questions?
No, clear, clear.
Okay, and these have a actually very important consequence in the quantum Hall structure of graphene. Okay, which has been observed in many experiments nowadays. So this sublattice picture will also be important there. I mean, the Landau level where it is lived on A sublattice or B sublattice and so on. And if you break some of the symmetries, for example, inversion symmetry, then it turns out that the clear picture that in the K prime valley, it is the wave function living on the A sublattice. In K valley, the wave function lives zeroth wave function lives on the B sublattice. This gets destroyed actually. Okay, once you break the inversion symmetry. Yeah, so this was it for today. If we have no question, we can conclude.
Yeah.
Yeah. Okay. So next day we'll study the quantum Hall effect in graphene. I'll try to finish it the next day itself. If few things remains, then I'll go to their next class. So what I'm trying to, I think what I can cover, given that we have only 3 class left, is that I'll study quantum Hall effect in detail as much as we can, and then study quantum anomalous Hall effect, and then quantum spin Hall effect. I don't think fractional quantum we can do actually, because fractional quantum Hall, at least it will take 3 lectures itself. So there is no point starting and then leaving in between. And fractional is anyway much more difficult to understand. So let's try to understand whatever we can cover more with more details basically. Okay.
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 Okay. Okay. Thank you.